All right, so this example involved, right, hot air from the hairdryer flowing upward. The ping pong ball located somewhere above the hairdryer. Now, this air that's flowing upward continues flowing upward in this method, or in this fashion. Yet the air outside of it is not moving. The air in here, though, has some velocity greater than 0. Now, if the air in that channel, this is a cylindrical channel. Take a look at the end of the hairdryer. It's a circle, right? So when I turn the hairdryer on, it's going to blow towards you with a cylinder of hot air coming at it. Take a circle and extrude it into the third dimension, you get a cylinder. So there's a cylindrical cavity or area or volume, space I should say, above the hairdryer. Take a look. Above the hairdryer. In that region, the velocity is greater than the region outside of it. And we know from Bernoulli's principle that when the velocity is greater, the pressure must be lower. They're indirectly related. So this becomes a low pressure area. God bless you. Over here is normal pressure. It's not high pressure, it's just normal. It's atmospheric pressure over here. Normal is higher than low. Even though we don't have a number for these, inside of that cylindrical area, region, space, inside of here, the velocity being higher causes lower pressure. When there's an imbalance of pressure, there's a net force acting from the higher pressure to the lower. So I'm going to draw a force with a yellow arrow here. So what this means, and it's hard to see this on the board, so I want you to look here also. What it means is this. In that cylinder above, there are pushing in from every direction. The higher pressure out here and the lower pressure in this little channel causes a force acting inward. So when this happens, you spun the ball a little bit, you can kind of see it oscillating back and forth. You can see in the beginning, especially when I put the ball in. In the beginning, especially, we notice that the ball starts to oscillate back and forth. Imagine gas particles in a balloon. Gas particles move at high velocity. They bounce off the container. That's what's happening here. Here's the container, ready? From your perspective, it's not going to work this way, obviously. But it would be like this. It would be bouncing back and forth because the cylindrical space around here acts as like a wall. Higher pressure out here. Again, higher pressure out here, lower pressure where the air is. So the higher pressure pushes it back in. So every time the ball wants to leave, it gets pushed back in, push back in, push back in. And what's keeping it up in the air is the force of the air pushing up and balancing the weight of the ping pong ball pushing down. Okay? So it's physically what's happening, so you can see that. And this is Bernoulli's principle. Okay? It's the same concept that gives us lift force so that airplanes can operate. Helen?
Does it have to be hot air or can it be cold air?
It could be cold air. It's all about the velocity. The velocity of the air that's flowing is what's causing the lower pressure in that little chamber. The temperature isn't really doing much there. All right, so let's open up the floor for questions first, as always. We've got really two ideas, magnetism and buoyancy, or magnetism and fluids, I should say. Those two ideas. Helen, go ahead. 12-2, number 77. I think I have that open actually already. For 78, the container is closed. So let's go ahead and import this so we can see it. So let's take a look. We're trying to find the depth of the fluid, right? Depth of the fluid. So in this problem, we're looking for H right away. The only thing for a depth is H. It's really the height of the water, right? Depth of the fluid. we're told that the total pressure at the bottom is 116 times 10 to the third pascals. Where am I getting 10 to the third? What is it? Good. Kilo, right? Kilo. So 116 times 10 to the third. Kilo means 10 to the third. Kilo means 10 to the third. Kilo means 10 to the third. Now, we also know that it's open to the atmosphere and we have a fluid density given. Helen. Have I ever been a stickler about that all year? All right, so let's keep going. So the density of the fluid is given as 806 kilograms per cubic meter. Let's see. We know gravity is always there. And because it says open to the atmosphere, what does that mean? What does that mean if we told that it's open to the atmosphere? Force? Is that the right word?
No.
Pressure. Good. We have atmospheric pressure is what that means. So we have to use P0 also, and that's 1 times 10 to the fifth. Is that pascals or kilopascals? Pascals. Yeah, kilo is the other one, 101.3. Yeah. All right, so that's what we know. And we have two options pretty much here. We can start with either looking at what's called total pressure, that being P0 plus rho GH, or we can look at what's called gauge pressure, which is just rho GH. Which of these am I going to use in this problem? You're told that it's open to the atmosphere. Which one? Yeah, we're going to use total. I mean, we're literally told in the problem that the atmosphere has an effect on it. So we have to consider the atmosphere. So we know the total pressure is here. We can write that in here. We know atmospheric is a constant. We can write that in there. We know the density. The density of the fluid is 806. We know gravity. Solve for H. Solve for H. So everything in that formula is given except for H, the depth of the fluid. Okay? All right, let's go to 7. Does that make sense? Can I leave that for you to solve? I don't have to go through the math at this point. Yeah. It's useless. Yeah, it's extraneous. Yep, that's a great point. 65.2 as the cross-sectional area had no effect on the problem. It's extraneous information. I think there was another example we had at another point in this problem set that was also giving you extraneous information. That's okay. I mean, it is something you'll see on a lot of tests like this, especially if you take like the subject or the AP exam, because the test wants to make sure you know what you're doing. So if they only give you all the information and all of it has to be used, it's almost too easy sometimes, you know? Think about it, right? Like you kind of have to know what you're looking for to know what you're getting. So if I'm looking for a force, mass and acceleration should be enough. I can use those two. But if I give you mass and acceleration and then I give you like electric charge, but you're not finding electric force, you need to know that that's extraneous, right? So you'll see that in some problems, and that's what this case presents. How does this differ from 78? 78 is pretty much the same problem, but there's one major difference. There's one major difference in 78. It's closed. It's closed. So what kind of pressure am I going to use? If it's not open to the atmosphere has no effect. So what do I use, everybody? Gauge pressure for that. So for number 77, we're using this formula, but for 78, we're using that formula. Again, P0 is just the idea that, hey, the atmosphere is open to it, so the atmosphere pushes down on it. But you know what? The atmosphere, you know what it does? It pushes down on the container, but not on the fluid. Okay, not on the fluid. The container walls push back. The fluid doesn't get that push, that pressure, that added pressure. How about part B to number 78? Part A you can figure out on your own. That's just numbers. Remember, oh, by the way, for part A, 6.4 is extraneous too. This number here is extraneous. You don't need it. You're told, or you're asked for the pressure 4.5 meters below the surface. So for number 78, your H is going to be 4.5 meters, not 6.4. Okay, 6.4 again is the full depth of the water. But it says, what is the pressure 4.5 meters below the surface? So your depth is definitely going to be 4.5. And we're told that it's fresh water. So what's the density of fresh water? 1,000. All right, so how about part B? Sorry, part B. Yeah, go ahead, Elias.
As depth increases, the pressure increases, and the reason that the metal bands are so close together is just because like it needs more structural support to actually keep the line.
Yeah, that's exactly. Great explanation. Great explanation. It needs more structural support in order for it to maintain its integrity. These bands are closer spaced because there's going to be more pressure as we go deeper in the fluid. So there's more pressure pushing out against all of these walls down here than there is pressure pushing out up here. This is less pressure at the top, and this is more pressure at the bottom. Okay? If you want to know, I said this this morning at office hours. Look up the Boston Molasses Massacre. Not the Boston Massacre. Molasses, like syrup. This is literally this example right here. You think you like syrup until you read about this. People died. There were tidal waves of syrup through the city. We're talking 30-foot waves of maple syrup coming at you. Imagine that. Okay? They had vats of molasses, and they didn't seal them properly. Where there was what was called rivets, there were seams. There was a metal vat. It was curled, and there were rivets along the seam. The rivets split. The molasses literally covered the city. It was crazy. 11 people died. It was really nuts. You would think, right? Because molasses moves slow, right? But that much pressure in those vats, doesn't matter if it is. Pushes it all out. What is it called?
The physics of the Boston molasses flow.
And there's a YouTube video about it? Yeah. I don't know. I go over to my engineering class. We talk about catastrophic failures. Nobody would ever think. Because I talk about this. I say, we talk about stage levels. Like an elevator, if it fails, you're screwed pretty much, right? If an elevator fails. But if other things fail, it's not as big of a deal, right? If certain things fail, I don't know, if this chair fails, you're going to die? No. I would hope not. But if something like, a building fails, you're going to die. You're not going to survive a building collapsing. Nobody would ever have thought that molasses tanks need to be considered high security or need to be considered, this is level 4 security. And not security, I mean integrity. There are levels 1 through 4. Level 1 is it doesn't matter if it breaks. There's no humans involved. So a satellite in space failing, who cares? We lose money and stuff, but it doesn't cost human life. That'd be level 1 versus level 4 where human life could be easily lost if this fails. Yeah, we never think of that in molasses. What else? 77 and 78 were those two.
Can we go over 12
Yeah.
on the notes?
Go for it. Which one?
The first example.
Can you just show me real quick? Which one? Oh, continuity? All right, let's talk about that. So Paolo's asking about the continuity equation. So let's start by writing it on the board here. So here's the continuity equation. The first part says, area times volume equals area times velocity equals area times velocity. And that's fine. But then we talked about in class that this is really called the volumetric flow rate. I use that phrase, volumetric flow rate. So this is volume as a function of time on the far right over here. So these are all equivalent to each other. But again, this is called volumetric flow rate. And volumetric flow rate is simply how much water or fluid is flowing. And I talked about, actually with you guys I didn't, but at the gas station this happens too. When you pump up your gas, at the very end when the tank is getting toward filled, it slows down the amount of gas that's pumping into it. Or if you go inside and pay with cash, you give the guy $20. When it gets to $19.90 worth of gas, it automatically throttles the gas and slows it down. And the volumetric flow rate decreases and less flows in. And you see the money go up until it gets to 20 and then it stops. You can't use it anymore. When I was younger, you always paid in cash. You can use a credit card at the machine. Now it's a lot of credit card. But that's what volumetric flow rate is. It's like turning the sink on and measuring how much water is flowing in. So this example is asking us about a pipe that either narrows or widens. Either one, right? Either one. By the way, this is why I recommend that you at least start the lab tonight. I'm not making it due until Saturday, you noticed, as I mentioned. Saturday is the due date for that lab. But I recommend that you look at Lab 17 and start working on it because it will help you for a problem like this. One of those applets involves changing the cross-section of pipes and using speedometers and pressure measures, pressure gauges, barometers, to measure how much pressure and velocity, and it shows this. Now, what we're seeing is an example that could do this, where it narrows, right? Or where it widens. So in both cases, let's assume velocity is to the right. So where it narrows, the cross-sectional area is decreasing. If that happens, then it has to speed up. Because again, in the beginning, I've got area. Let's say the area is 2. I'm going to use easy numbers without units for a moment. And at this moment, let's say the velocity is also 2. And then suddenly the area becomes 1. I'm using very simple numbers on purpose. What would the velocity be at that moment? Well, it's just a product law. Take a look. In the beginning, what's 2 times 2 is just 4. So then 1 multiplies by what number? It'll also give me 4. It must be 4. So if I take the area and halve the area, I double the velocity. I double the velocity. And again, what am I doing? I'm plugging them in right here. So, how are these related? How are these related? Area and velocity. How are they related? What is it? Look at it, right? You tell me. Area decreases, yet velocity increases. Indirectly. It's all right, write it down. Indirectly related. So, the second scenario given here would be the opposite. It'd be going really fast, and then it opens up, and it will slow down. The flow will slow down. Okay? Now, the problem that Paolo was asking about is from the notes, and you could use that example. It's a good example. That has an example where I'm giving you a radius, right? So what kind of a cross-sectional shape would it be if I give you a radius? What's the cross-section? It's a circle. If I give you a length and a width, what's the cross-section? What shape has a length and width? Or, more general than a square? Rectangle, we'll say, but quadrilateral, yeah. So I can tell you that the cross-section is a rectangle, and the length and width are given of that cross-section. And then the cross-section changes because the length and the width both half. And then you've got a new length and width, calculate a new area. With the new area, you've got a new velocity. So I don't want to do just this example. I want to explain to you that any shape cross-section would work. So if the shape is a circle, your area, right, in this formula becomes the following. Pi r squared. This is the formula if it's a circle. All right, that's a circle. For a rectangular cross-section, it would look like this. L1, W1, V1 equals L2, W2, V2. And how do I know that? Because how do you find the area of a rectangle? Length times width. So I'm replacing area with the equivalent cross-sectional formula based on the shape. If it were a triangle, you would use for the area 1/2 base times height. Is that clear what I'm saying right now? So based on the cross-section of the pipe. So I want you guys all to visualize this. How can I make you visualize this? All right. So this cross-sectional area for this pipe is clearly a circle, right? We all see that? It's obvious. But something like this is piping that has a rectangular cross-section. So if you see an image on the test tomorrow that looks like this, and you see a rectangular solid, and I tell you that this is ductwork. Ductwork is the ventilation system above you that pushes air through the ceiling. Now, in this building, we don't have that. We have air conditioners and heating. But a lot of buildings have what's called forced air. So in the ceiling, you have all these rectangular metal chambers, and air flows through them. That's what you're looking at right here. So this would be a rectangular cross-section. I would use the top formula there. So depending upon what the shape is of the cross-section, I might have to use a formula for the area at that spot. Okay? Area at that spot. They're indirectly related. Hey, how about Bernoulli's principle here? Let's talk about pressure. We just spoke about it a moment ago with the hair dryer and the ping pong ball. But if the velocity, so we're going to look at the first case. Forget this one for a minute. So if the velocity increases, what did we say happens with Bernoulli's principle? Yeah. So this is a low pressure here, and this is a higher pressure here. And that makes sense. When you put your finger over the end of the garden hose, doesn't it spew out of the garden hose? Because there's more pressure built up behind it. This pressure that's here is physically forcing the water out. That's why it's accelerating it forward. And therefore it's increasing velocity. Okay? That gets covered, that pretty much covers a lot. Yeah, a lot, if not all, of 12.3. That example right there, when you think about it, right? That's all of 12.3 right there. It's not much more. 12.2 had a lot more math. Hydraulic lift, pressure as a function of depth, which we did, 77 and 78, and then density and buoyancy and that stuff. What else? Did anybody notice under documents and handouts I put some sample problems? If you haven't gotten to those, I think I might have mentioned it, but if you haven't gotten to them yet, tonight's a good night to look at them. Under documents and handouts, you'll see 12E. It's just example problems from 12.2 and 12.3 with solutions written for them. Really good examples to look at for this test. Okay? Really good templates for this test. Yeah?
81 on 12.2.
What is it?
81.
Okay, let's take a look at 81. We're thinking of an air mattress right now. It's floating on water. You've all slept at some point, like at an air mattress at a friend's house or something like that. Maybe, maybe not. I'm seeing now, yes. Okay. It's an inflatable thing. So we assume the air mattress has a certain size or capacity to it. So here's what I'm visualizing. Okay, that's what I'm visualizing. And I'm told that it's 2.3 meters long, it's 0.66 meters high, and 14 centimeters deep. Right away, what do I have to do? I can't hear you.
Get the area of the...
Before that. We could do that, but before that. Come on. First thing. What do you notice? 2.3 meters. 0.66 meters. Kevin?
Put it in on the same unit.
Yeah. This is 0.14 meters. Right away, please correct that. It's the first mistake I've seen on this problem because a lot of people struggle with this and they asked this morning. Now, after that, we have to start considering what's happening. So, first, what is the maximum mass this can support? So what's going to happen, right? This air mattress has its own mass. Let's say the mass of the mattress is 0.22 kilograms. That's given in the problem. I'm giving it a subscript, MM, mass of the mattress. It's given in the problem. We are given the length, width, and height. So what are we technically given if we're given length, width, and height? Volume. We're given volume also. Okay? Now, suddenly, mass is placed on top of this. Whatever it is. Gold coins. I don't know. Okay? But masses are placed on top of here. The assumption is that these masses do not add to the volume. That's the key to this problem. Because I can add mass and figure it out in a moment. But if I don't know the volume of those masses, then I really can't do this problem. So we assume that when the masses are placed on the mattress, the volume of the mattress doesn't change. It doesn't sink in. It doesn't push down on the mattress. It remains the exact same shape. That's the key we have to consider. Why is that? When would an object be able to still support something else before it sinks? When does it eventually sink? How about that? When will this mattress eventually sink?
When the density is less than the weight.
Close. You're on the right track, but you're mixing things up. Have Nick help you out a little bit.
Generally speaking, the force pushing down is less than the force pushing up. Sorry.
Force pushing down.
Up is,
More than the force. That's one way to do it. But let's go back to Paola's answer. I like the idea of density. More, you want to help her out?
So the density of the thing on the mattress is greater than the water itself.
Then water.
Yeah.
Remember, if you're going to,
FG is greater than FB.
that's one way, but you said density. So density is the row. So there's two options. Remember, things sink when you have this. You could have this causes sinking, and this causes sinking. Both of those, right? So we can approach this either way. We can approach this by trying to figure out the weight of the mattress and see when it's more than the buoyant force. I think that's a lot of work. It's a lot easier just to do it this way. What are we resting on? What kind of a fluid? What does it say? Fresh water. So what's the density of the fluid? 1,000. Fresh water is 1,000. You don't have to memorize it, but you probably know it by now. So our question really is this right here. This object will no longer be able to support itself and that mass when its density is more than 1,000, right? What is its current density? What's the current density before we add in these gold coins? I don't even care about a value. I just mean, how would you calculate its current density? Go ahead.
You would take the volume and then you take the mass of 0.22 kg over the value you get for 0.14 times 0.66 times 2.3.
Good. So LWH is the volume, and the mass is given, right? Now tell me real quick. Calculate this. The mattress by itself, is it going to sink? Is this going to be a number more than 1,000, you think? Definitely not. You could just see it, right? Everybody agree with me? You're taking a number like 0.22 and dividing it by another number that's bigger. Or a number that's, well, maybe not greater than 1, depending on what happens here. But it's not going to be greater than 1,000. You can tell by just inspection. You don't have to do the math. But what are we doing to this mattress? We're adding what to it? In this case, we're going to say mass. But yes, weight works. But mass, because we're using mass here. So what I need to do is recognize that the gold coins do not contribute any volume. Remember I said that a moment ago? We're not adding volume to the mattress, just mass. So put this, please. And let's make sure we use our subscripts properly now. That's why I called that MM earlier. So that's the problem we have to solve, really. When is this expression right here greater than 1,000? Again, the mass of the mattress plus the gold coins over the volume of the mattress, that'll give us the density of that combination. When is it going to be more dense than water? When it is, it sinks. The same thing happens with a rowboat. Now, with a rowboat, you have a tendency to go a little bit lower in the water every time. But if you eventually have too much mass in the rowboat, what's going to happen to it? It will also sink. Is that clear what I'm saying? Yeah? Okay. So let's figure out what that becomes. Let's plug in. So to finish this off, what would I do? I would take that expression and set it greater than 1,000. And you have to solve this. And yes, it's an inequality. That's fine. Inequality is not hard to solve. Solve it the same way as an equation. Get a number for this right here. Multiply it up by 1,000. Subtract the 0.22. And you'll get an answer that says mass must be greater than some number. And that's what we're looking for. We're looking for the threshold limit, finding the mass that causes this object to sink. Okay? When it can no longer support it. What is the maximum mass it could support, which means when it actually sinks. Guys, today's day 6, right?
Yeah, we're done.
Okay, that's fine. Okay. Yeah.
For this problem, could you just set it equal to 1,000 because it's like
Sure. And you could solve for m, and that'll give you the maximum mass it could support. Anything more than that, though, it sinks. Yeah, you could use equal. That's fine. But at that moment, it won't sink, right? It'll still float, or it'll be like that in limbo stage, where it like starts to sink, but it like just finds a spot. What else? What else? What other questions do you have? Conceptual, mathematical. most of 22 magnetism is conceptual, very little math, more like direct and indirect relationships that exist. Helen? 91?
Yeah.
It's the hydraulic lift. So hydraulic lift, the idea is that the system is closed. So what's happening is you've got like a piston right here that can move up and down, and another piston right here that can move up and down. Now, inside of this is a fluid. Oops. And that fluid has pressure, has hydrostatic pressure in it. So when I push down on this end right here, and I apply a force F1, that force gets transmitted to the other side through the fluid. Remember the unbreakable egg I had you guys, I said if you want to do? So the unbreakable egg is the same concept. The force you're applying is getting transmitted to all parts of the inside. So right now, inside of this chamber, there's a force pushing here, pushing here, pushing here, pushing here, pushing here, pushing here, here, and here. And when the force pushes here, what does it do to this piston? It lifts it up. So the thing is this. The forces are not the same everywhere. The pressure is the same. Pascal's principle tells us that the pressure exerted outward in a closed system is equivalent on all parts of the system. So you see I'm drawing all these arrows acting outward. Every one of those red arrows acting outward is showing pressure, pushing out. The pressure at any location in a closed system is the same. So pressure is defined as force over area. So if I could find the force over area here and the force over area here, since the pressures are the same, the force over areas have to be the same. So that's where this statement comes from to start, and then this becomes this, and this becomes this. So then, from that part, you just manipulate the formula based on what I give you. If I give you the areas, you plug the areas in. If I give you the force you push, you plug it in. And then you can see the force that comes out. If the force that comes out is double the force you put in, that's a mechanical advantage of 2. If the force that comes out is triple, 3, etc., etc. If I don't give you area, but I give you a radius or a diameter, you need to know that the area is pi r squared. That's the most common area you're going to plug in for. Whenever I don't give you an area, but I give you a radius or a diameter, you're going to have to use that in the formula for area. So replace area with pi r squared if it's a circle. And these problems with the lift are always circles, the hydraulic lift problems. Okay? Hey, listen, I would recommend 2 things. 1, look over 22, the conceptual stuff, because that's where it's going to play a role. Know how magnetism and solenoids with the wrapping of the coils, the more wrapping of the coils, the stronger. That's why you get that decent motor lab with this. 2, I would look at the 12E problems that are on there. Okay, if you got started in your lab, that's good. I'd recommend it, but it's not mandatory.